All right, so it's my pleasure to introduce Inbal Talgam Cohen, who's here from Stanford. She's a PhD student in Tim's group, and she's going to present her recent work on interdependent types and mechanism design for players of independent types.
Thanks a lot. Okay, so yeah, thanks for inviting me. And this is I'm going to present joint work with Tim Roughgarden that appeared in EC13. Okay, so I want to start by asking you, how much would you guys be willing to pay for this painting? Any bids?
$40.
40?
Yeah.
Okay. Anybody care to?
Can I resell it?
Thank you.
You can definitely resell it. Yeah.
In
You can
that case, I'll
definitely
do
resell it. Okay. $40 is the highest. Okay.
Pay 41.
Well, well, if you were to buy this painting for $41, you would be making a great deal. This painting was sold earlier this year for $43 million after a close fight between 6 bidders. How do we explain this kind of phenomenon? So here's a quote from the guy at Sotheby's who ran this auction. People are very educated, they know what is what. And this kind of leads me to the subject of the talk. So in the AGT community, not so much in econ, but within our community, we usually look at independent private values as the model for bidder values. In this model, your value depends only on your personal kind of unbiased opinion for the item for sale. And this model doesn't seem to really capture, what's going on behind these high-stake auctions where people bid so much for the item for sale. So I want to give 2 explanations to what's going on in this high-stake auction. So here's one scenario. The person who bought the painting for $43 million, he's an art enthusiastic. His value, does depend on how much he loves the painting, but he happens to really, really love the painting so much that he's willing to pay this high price. And it happens to be, that 5 other bidders also have this very high value for the painting. So what I want to say here is that, it's no coincidence. So there's some kind of correlation going on between the personal opinions of these bidders. And, art lovers will tend to like the same pictures or dislike the same pictures according to some unknown artistic value. Then another explanation is the reselling thing that you guys mentioned. So, maybe the buyer personally couldn't care less about a white stripe on a blue background, but he values the painting really highly because he could resell it. He knows he can resell it. So in this case, his really high value for the painting that translate to such a high bid is because his value is a function of opinions of other bidders who would eventually, or other people on the market, people who would eventually maybe buy the painting from him. Okay, so the first scenario is why we consider beyond independent values, and the second one is why we consider beyond private, because there's this common component to their values. Okay. So values that involve either correlation or have this common component or both are called interdependent values. This is a kind of a very classic model in economics. It was developed by Milgram and Weber in their 1782 paper. And it goes back, the roots even go back to earlier to the work of Bob Wilson on pure common value auctions for oil drilling rights. So either there's oil or there isn't, and everybody values high or low depending on this. So the theme for the talk is going to be, first of all, that if we expand AGT research beyond IPV to interdependent values, this can be fruitful. So I hope I kind of convinced you it's important, right? It models high-stake auctions that involve a lot of money. it raises new technical challenges for us to kind of overcome, hopefully. Yeah, and the thing is that with the right assumptions, I'm going to convince you in this talk, I hope, that it's not hopeless. You can get positive results. So in particular, I'm going to show, I'm going to discuss this theme in the context of revenue optimal mechanism design. So our basic tool for optimal mechanism design is the Myerson theory of optimal mechanisms, and I'm going to show how it extends to interdependence. And then there should be also, since Myerson's theory has a lot of applications, we expect to see them extending as well to interdependence, and I'm going to demonstrate in this talk with the application of prior independence. And there's also been kind of parallel work of Yunnan Lee about simple versus optimal application for interdependent values. A second theme of this talk is robustness. So I want to claim that robustness is an important design concept when we design mechanisms, in the sense that if you design a mechanism that's not robust, that is, it assumes that either bidders or seller know a lot about the environment and the distributions in the environment, this can be unrealistic. And actually, you can get a considerable level of robustness in single parameter environments without giving up too much on functionality of the mechanisms. And by the way, this is not the case for multi-parameter, where we know there are very kind of strong hardness results that you can't do a lot if you try to impose robustness. And interestingly, I'm going to show how the two themes of robustness and interdependence are kind of related. Okay, so I'm going to introduce Milgram and Weber's model more formally. And then in the first part of the talk, I'll show Myerson's theory beyond IPV. And the second part of the talk, I'm going to talk about prior independence beyond IPV. So are there any questions about the introduction part? Okay. Okay, so let me show the model. Okay, so the classic Milgram-Weber model it is a model for single parameter settings, as I mentioned, so you can just think for now about a single item for sale. And in this model, bidders have privately known signals. We're going to denote them by S sub 1 to S sub n. And each bidder's value is a publicly known increasing function of all of the signals. So V sub I is a function of the signal profile. Okay. We're also going to assume as part of the model that we're in a Bayesian setting. So the signals are drawn from some publicly known joint distribution that we denote by capital F, and it has density F. Okay, and this is an important assumption of the model. Signals are assumed to be what's called affiliated. So this is first of all, I want to kind of emphasize that this is a standard and prominent assumption in the econ literature. And what it assumes is some form of positive correlation among the signals. So, so what you see, this inequality is the formal requirement. But really what you should keep in mind is the intuition behind it, which is that if you have a profile of signals, which you don't know, you only know like part of the signals, and you know this small part of the signals is high, then the other signals tend to be high as well. And if you know some signals and you know they're low, then other signals tend to be low as well. Okay, and the inequality, I mean, it's there, so it's nothing more than that, but it's not going to matter too much for us in this talk. Okay, so going back to the painting scenario, how does this model kind of map to it? So the signals model the private opinions of the bidders for the painting. They're kind of naturally affiliated, as we discussed. They all love the painting or hate the painting more or less in a correlated way. And the values, there are functions of everybody's opinions for reselling purposes. Any questions about the model so far? Okay, so let me point out something really weird about this model. Bidders may not know their own value because it's a function of the signals of everybody else, and the signals are private information. We're going to be focusing on mechanisms that are direct and truthful. So everybody's going to report their signals to the seller. And the seller has all the information. He knows the valuation functions, and therefore he can kind of act on behalf of the bidders. So we do have information externalities here, but we can also deal with them by the mechanism design. Okay, and now I want to finish this model part by showing you an example. So signals, let's say the signals are just distributed according to a normal distribution, symmetric normal distribution, the marginals are all the same. Let's say that the pairwise covariances of the signals are non-negative, which is enough in this environment to guarantee affiliation. And then the values are going to be, in this example, just weighted sum of the signals. So value of bidder I is going to be the sum of his signal plus some weighted sum of the other signals. So as you can see, if beta here is 0, then we get that the value of bidder I is just his own signal. He only cares about his own opinion. If beta is 1, he kind of gives equal weight to all of the opinions of the bidders. Mm-hmm.
And beta is just between 0 and 1, irrespective of n, the number of bidders?
In this example, yeah. In this example, yes.
Okay, because so that would allow you to have very small knowledge from your own signal.
Sorry?
Your signal might be a tiny part of what goes into
right. If there are a lot of true, yeah. You could also think about, right, I guess averaging wouldn't solve what you're saying, yes. In this example, if beta is 1.
If it works, it works.
I guess if you vary beta is closer to 0, then your signal has a larger part, and if it gets closer to 1 and there are a lot of bidders, it gets really tiny.
Yeah.
Okay. Okay, and just kind of to point out that in this example is all symmetric, because we have this symmetric distribution, and also because the values, the way they use each bidder's signal is the same for all of the bidders. Okay, so now I want to go on to the kind of first part of the talk and discuss Myerson's theory. Any questions about the model? Okay. Okay, so I want to show a really quick reminder of Myerson's theory, mostly to kind of set the terms that I'm going to be using throughout this part. So recall that Myerson's theory goal was to design mechanisms that optimize the expected revenue. This is subject to some no-regret requirements, namely IC, which is not regretting being truthful, and IR, which is not regretting participating in the auction. So Myerson laid out his theory in 1981 seminal paper, and he got the Nobel Prize in 2007 with Horowitz and Laskin for having laid the foundations of mechanism design. Here's kind of the heart of Myerson's theory, according to Wikipedia. His main contribution was to kind of find out this fundamental connection between monetary transfers and allocation that you need to get truthfulness. And throughout this talk, I'm going to refer to this as his characterization result. So kind of in our language we're more familiar with, a direct mechanism will be IC and IR if and only if we have A, monetaricity of the allocation rule, and B, we have payments that are somehow derived from the allocation rule. And then Myerson goes on to kind of give us a handle on revenue. So this is IPV model, remember, so we have the values that are drawn from distributions, and then you can define the virtual values in a way that very heavily uses the distribution. And then what I'm going to call his expected revenue result is to say that the expected revenue of the mechanism is equal to the expected virtual surplus. So you look at the allocation of the mechanism, and you kind of sum up what the virtual values are of whoever won in the auction. And this gives you the expected revenue. And from this, you can also derive what the optimal mechanism is. So the Myerson mechanism, the optimal mechanism, will maximize virtual surplus. Okay, that was like a really quick reminder. And now I want to go beyond IPV. And here we start discussing the issue of robustness. And I want to show like why robustness even arises. So, okay, our goal is to kind of take the Myerson theory and beyond IPV. And here's an obstacle. So if you have even a tiny degree of correlation among the signals, then the Kramer-MacLean mechanism knows how to extract full welfare as revenue. And this has been criticized as unreasonable because it's high sensitivity to bidders' beliefs about the signal distribution. So it kind of makes the bidders participate in these really high-stake bets on what the other bidders' reports are going to be. And so their willingness to participate really depends on what they believe about the other bidders' signal distribution. And this sensitivity has been criticized. And the conclusion is that you kind of might want to strengthen the robustness requirement. Okay, so remember that you can look at different levels of robustness to bidders' beliefs about the signal distribution. So this will give us kind of different levels of IC and IR no regret requirements that you can ask the mechanism to satisfy. So, so the first one is kind of the standard one, Bayesian IC and IR. That means that you will not regret participating truthfully in expectation over everybody's signals. And then we have ex post IC and IR and dominant strategy IC and IR. These are the same thing if we look at IPV model or even with correlation, but with full interdependence, they become separate things. So the first one, ex post IC and IR, it means that you will not regret participating truthfully, no matter what the other bidders' signals are, but they do have to be in equilibrium of participating truthfully themselves. And the dominant strategy just means that you don't care what they do. And dominant strategy can be shown to be really, it's very strong requirement, and you stop being able to get meaningful results. So we're going to concentrate on ex post ICIR. Okay, so why doesn't this all come up in the IPV model? Just because Myerson is really Myerson mechanism is really cool in the sense that it's dominant strategy IC and IR, so best you can hope for in that respect. But it's optimal among the very wide set of all Bayesian IC and IR mechanisms. So it's the best you could hope for. It's like the best of both worlds, and there's no trade-off between robustness to bidders' belief and optimality in the IPV model. Okay, so this is really remarkable, and indeed it doesn't hold beyond IPV. So beyond IPV, we start having this classic trade-off. So you should decide if you want perfect optimality, in this case you should use the Kramer-MacLean Bayesian IC and IR mechanism, or you want to kind of shift along the axis towards robustness, and then you focus on ex post IC and IR. And that's the solution concept we focus on. So first of all, we believe it's more reasonable for kind of reasons I explained, and I'll also talk about this a little more in the second part of the talk. And the second thing is that once we focus on ex post mechanism, this enables to get analogs of Myerson's characterization and expected revenue results for interdependent values. And this is actually known in the economic literature. We found it in a lot of different kind of places, but this is known to hold. And then the question is, okay, you have the characterization, you have the expected revenue result, we want to get the optimal mechanism. So we want to get like a Myerson-like mechanism, and can you do that? Is the natural analog of Myerson always optimal? And we kind of know in advance it's not going to always be optimal, and here we have a computational consideration. So from work of Papadimitriou and Pirakos, we know that if the problem of finding ex post optimal deterministic mechanism, and Myerson is deterministic, that is NP hard. If you look at even 3 bidders, 4 bidders, anything beyond 2 bidders, it becomes a hard problem. So we're not going to expect the deterministic Myerson mechanism to be the answer always because we have hardness.
So, by the way, this result, though, that's for deterministic mechanisms, and Myerson's mechanism was not constrained to be deterministic. Like your ex post IC and IR, it just happened to be that way.
Yeah.
Right? So it's another coincidence. It just works out that in the single-dimensional IPV model, the optimal mechanism happens to be deterministic. And so here, for correlated types, the optimal mechanism is randomized. And that mechanism is easy to find always, or in their setting. And so this result is kind of...
Wait, what do you mean easy to find?
It's easy to find. It's not NP hard.
Well, I mean, so it's easy to find for a constant number of bidders. I don't know for a large number of bidders what you would do for non-constant.
So it's also easy to find in the... So if I tell you the distribution exactly, then I have to give you an input of size that's then large in the number of bidders.
Right.
So it's always easy to find. And so this is kind of out of context, right?
Okay. So first of all, I mean, I don't know if, giving the whole distribution is like, is the kind of thing we would really hope for. So what I would say we hope for is more like a result along the lines of, there's Ronan's look-ahead auction, which, work by Fu et al. Shows that it gives really good approximation for the optimal revenue in a correlated environment. So not full interdependence, but correlated. So that I would consider like a really cool result that one of the open problems I think that comes out of this work is that maybe we can do this for interdependent, but I don't know how. The look-ahead mechanism doesn't work. But that's like an example of a positive result that doesn't need this reporting the whole distribution, which is a little bit artificial, or arguably at least. And then I guess the question here is, it's a natural question once you have part of Myerson's theory to see what the conditions are. Sorry, this is kind of my next bullet. So what are the sufficient conditions so you can push the whole theory through and get this form of Myerson-like mechanism, which is, it's also useful for us because we have a lot of results that are based on it, so we can kind of hope that other results will follow as well. So I definitely agree, it's a great open question to think about, meaningful mechanisms that are randomized and are near optimal or optimal. Any more questions about this? Okay. So now that we kind of know what the solution concept that we're focusing on is, I want to show the sufficient conditions under which we get the Myerson-like mechanism. I'm just going to quickly show you what the characterization result and expected revenue result look for in this model. So, direct mechanism for interdependent values is ex post IC and IR, if and only if we have monotonicity, which in this context means that as a signal of the bidder increases, he's more likely to win. And payments, it's just analogous to what we had before. And then we have an expected revenue result. So notice it's the same thing, but now we have what we call conditional virtual surplus, because I'm going to this is the form of the conditional virtual surplus, and I want to highlight, what's different. So you can notice that it's conditioned on the signals of all the other bidders, and then so you have the value that's also a function of the signals. You have the distribution, which is now joined, so you have to also condition, and you get this extra derivative term that kind of comes out of the math. And so the result becomes that the expected revenue is expected as a conditional virtual surplus. Okay, and now I want to state something about the optimal mechanism. So consider the following allocation rule. Maximize conditional virtual surplus on every input. So get the signals, translate into conditional virtual values, and give it to the guy with the highest one, or the highest non-negative one. So I want to say that if this rule I just described is monotone, then the corresponding mechanism with the payments that we know their form is going to be X post IC and IR and optimal among all X post IC and IR mechanisms. Okay, and then we know by hardness it's not always going to be monotone. And I'm going to show two conditions, regularity and single crossing, under which we get this monotonicity. Okay, so regularity is a little bit, I think we're all kind of more comfortable with this, and single crossing I want to show now what it is and why we need it. So let's say we fix the signals of all bidders besides the signal of bidder I, and now on the x-axis we're going to start raising the signal of bidder I. Regularity means that the conditional virtual value of bidder I increases as his signal increases. Now here's what could go wrong. So as you increase the signal of bidder I, because everything is conditional on all signals, then you could get that the conditional virtual value of a different bidder, bidder J, is also increasing. Let's say we're trying to give it to the guy with the highest conditional virtual value. Here's what could happen. So up to a certain point, I has the higher conditional virtual value and he wins. But from a certain point, bidder J starts winning. And this is a violation of monotonicity. So in order to have monotonicity with this allocation rule that gives it to the guy with the highest virtual value, you do need single crossing. It's called single crossing because you can see here the functions cross at 2 points. So that's what we kind of want to avoid.
So, given the problem here is given I's bid, J goes from winning on the far left to losing, and then to winning again as he raises.
Yes.
And therein lies the problem.
I mean, the problem is that I wins and I stops winning, because then I would want to shade his bid, right?
Okay.
Yeah.
Thank you.
Okay. Okay. And so then the final question is kind of identify conditions to get this single crossing. Okay, here we have kind of two levels of results. So first of all, if we only have correlation, so this is kind of the case where the value is depends only on a bidder's own signal, but they're correlated, then this condition of affiliation I described is just sufficient, and you get single crossing. If we have full interdependence, then there are conditions that we call Lemma conditions because they're found in a paper of Lemma in the context of English auction. And these are technical conditions. I won't go into them very formally, but they're conditions on the signal distribution requiring it to be MHR. And they're conditions on the value functions. So the values themselves need to be single crossing and some kind of multilinearity. I'm kind of hiding the details here, but I want to give you the just the feel of what these conditions are. And if these conditions, if they hold, then we have single crossing. And I want to just point out that in the example of the value that is a linear combination of the signals, then we have everything that's required from the Lemma conditions.
Can I ask a question? Can
Sure.
you go back 2 slides to the picture again? Is it calling it single crossing? Maybe I was just being picky about the language, but going back to Mark's question,
Right.
it could still cross once, but you'd still have the problem, right? What I'm saying is maybe is the term single crossing not the right term here? Is it?
It's got to cross the
You
right
only have
direction.
Oh, I see what
you
you
only
mean.
have a problem once.
I see what you mean. I agree.
Actually,
So the crossing is only from one direction.
Yes.
Similarly, is this supposed to be the virtual value for player J? Shouldn't that be a function of SI?
It's a function of SI that's hidden
In the
here.
second half.
That's hidden in this condition on
That's what's changing.
bidder I.
Yeah, but the point is we're looking at it
Yeah.
here as a function of SI.
I agree. I mean, maybe the notation is not perfect. I agree. I'm using single crossing just because that's like the standard term in the literature. Yeah, it is. It's also really ambiguous in the literature. You see like people saying single crossing, but they mean totally different things, and that's why I kind of wanted to take a step ahead and kind of spell out what the conditions are on the distribution and values that you get single crossing. Yeah.
Be the originator of the correct term. And then you'll be cited even more often. Whatever that correct term is.
Yeah, so if you have
It may
suggestions
be
after the
hopeless,
talk,
though.
please, yeah.
Standard setting is going too far to get a standard.
Okay, okay, so I'm going to kind of wrap up this part, and here's my take-home message from part 1 of the talk. So there is a Myerson-like theory for many, not all, but many interdependent settings of interest. And like in the IPV model, we expect this theory to have, a lot of exciting applications. And I'm sure you guys can come up with a few kind of applications of your own. Now I'm going to show one, which is prior independence. Okay, any questions about the first part of the talk before I go on? Okay, so I'm going to kind of switch gears. I'm now going to be talking about prior independence beyond independent private values. So what is prior independence? I understood from Jason, you guys know this, so I'm going to go over it pretty quickly. What we're going to do here is require even more robustness. So up till now, we've been looking at robustness with respect to the bidder's knowledge of the signal distribution. And from now on, we're going to require the same robustness to the beliefs on the signal distribution, but also from the seller. So this ex post ICIR requirement, it's still going to be necessary, but it's no longer going to be sufficient. Here are the mechanisms that we're focusing on. So we want to focus on mechanisms that are based on prior independence assumption. So whereas Bayesian mechanisms are based on the assumption that there's some publicly known prior distribution F from which the bidder signals are drawn, the prior independence assumption still assumes that there is some prior distribution underlying from which the signals are drawn, but now it's no longer public. So by that I mean neither sellers nor the bidders have access to this distribution. And so maybe they know that it belongs to some class of distributions like regular or MHR, but they don't know the details of the distribution. And this kind of affects what we require in terms of optimality. So requiring, let's say M is a prior independent mechanism, so requiring it to get, optimal expectation revenue would be too much because it doesn't have any information it can work with. So we kind of relax and require it to only extract an alpha fraction of the optimal revenue expectation. However, we strengthen the robustness requirement, and now we want it to extract alpha fraction of optimal revenue for every one of these distributions in the relevant class of distributions. So this is what I wrote here kind of more formally. So what we have on the left side is for every distribution F in the class, we want the expected revenue of prior independent mechanism M, where the expectation is taking over signal profile drawn from F, to be comparable to the optimal expected revenue. And I want to kind of stress that, this mechanism, the optimal one, has access to F and M doesn't. Okay, so that's like the challenge. Okay, and so what we did here is kind of move along the optimal versus robust axis more towards robustness. Okay, and this is kind of so what I'm talking about in this part of my talk is, the sole justification is robustness. So I wanted to spend another minute and kind of convince you more that this is worth sacrificing in optimality for. And maybe it will also convince, I think, some people may be skeptical even about the first part, so it's also a justification for that. So the first obvious reason to have robustness is sellers and bidders just may not know the prior distribution. So if the seller doesn't know the prior, how can he focus on a carefully tailored auction towards the prior? And if the bidders don't know the prior, then if they're faced with a Bayesian mechanism, they're not sure whether they should participate truthfully or not. There are also more kind of subtle reasons. So I guess it's reasonable to assume that bidders do have some kind of beliefs about the distribution. But it's not at all clear that the seller will want to kind of rely on their beliefs. So it makes sense for the seller not to want an auction that's robust to that. And also, it's just a lot more practical, right? If you have an option that you can reuse in different scenarios, and you don't have to kind of spend resources like learning the environment every time you reuse it, then it's more practical. And this has all kind of been known to, it's known as Wilson's doctrine. It's named after Bob Wilson and other economists who kind of called for the field of mechanism design to kind of steer away from these very detail-dependent mechanisms and look at mechanisms that are more robust to seller and bidder beliefs. Okay, anybody want to challenge this? Yes, I know Jason had some reservations, but we can also talk about them later. Okay, this is kind of very quick summary. So prior dependence is alternative to Bayesian approach. You lose something in optimality, but you gain in robustness, both with respect to the seller's guarantee, so it's optimal for a class of priors now, not just one, and with respect to the bidders, kind of no regret, you give them ex post instead of Bayesian. Okay, great. Okay, so I want to quickly go over previous work and show you the setting that the results are going to be in. So previous work on prior independence has kind of gone in two main directions, or that's at least one way to look at it. So when you think about it, how are you going to get a mechanism that doesn't use information to perform almost as well as something that does use information? And the answer is that you get the market to do more for you. So kind of the first line of work is along increased competition. So you make up for no knowledge just by increasing competition. You get almost as good revenue. So this was kind of pioneered by Bull and Klemperer. And then the second line of work is that you look at the market and you try to kind of see what the bidders are doing and kind of extract from their bids, empirical knowledge about the distribution. And this was pioneered, I think, right by Goldberg et al. And there's been a lot of work since then. There are also other works on prior independence recently. Okay, what I want to point out is that all of these works, and our work is not going to be an exception to this, they all rely on the symmetry assumption. So we assume that the signals are all drawn from the same distribution, or at least, there may be several distributions on the market, but you have to have a few identifiable representative bidders from each distribution, because without that, we don't really know what to do. And okay, so we're going to assume symmetry in this setting from now on. Okay, now I want to talk about beyond single items, so I want to kind of move from paintings to photography, and this is I guess the most famous photograph in terms of how much revenue it got in an auction. So a couple of years ago, it got something like $4 million. Okay, and so I guess you guys wouldn't have won it in auction either. Okay, so let's look at the setting. So we have a symmetric, what's called a Matroid environment. So we're still in the single parameter world. We have symmetry, as I explained. And what we mean by Matroid environment is that the sets of bidders who can simultaneously win, these are called feasible sets of bidders, they form a Matroid. So here's a quick example. If, say, I have 3 bidders, and I have kind of 2 copies of this photograph, and what you see circled is a feasible set, and other sets of 2 bidders are also feasible because we have 2 copies. And so this is like a 2 uniform matroid, a very simple matroid. And the advantage of matroid environments that make them kind of interesting for us is that if you want to find the feasible set of bidders with the highest signals, then you can just do it greedily, right? You just go over the bidders and you add the next bidder with the highest signal if that doesn't ruin feasibility. Okay. Any questions about the setting? Okay. So I can now state our contribution. So we focus on a symmetric matroid environment. And what we show is that there exists a prior independent mechanism for non-private values. So it gets what we wanted, the constant fraction of optimal expected revenue. Sorry. Okay, so it manages to extract a constant fraction of optimal expected revenue even though it doesn't know the distribution. Since we're in this non-private value setting, we do need the Optimal conditions from part 1. And I'm going to give you an example showing you why we need MHR at least. In fact, actually I'm going to prove something a little stronger, so we get a constant fraction of welfare by this mechanism, and this is kind of very characteristic of MHR distributions. It kind of just follows from that. Okay, so let me describe the mechanism. So say I have my bidders. So what I do is I uniformly at random, I pick one of them. I set this bidder aside. This bidder will be denoted by R. Now I look at all the other bidders, and I find the feasible set of bidders from these bidders with the highest signal. And this set I denote by capital W because these are like the potential winners. Now how do you become a real winner? If you're in the potential winner set and you manage to clear the reserve, so your signal is higher than the reserve bidder signal, then you win. Okay. Why is it called a single sample mechanism? So let's just, to get the intuition, think of a single item auction. So we know what the optimal mechanism is because we have, the results in part 1. So because we have a symmetry assumption here, just like in the IPV model, when we have symmetry there, then the optimal mechanism is just second price auction with reserve. Here it's going to be English auction with reserve. The reserve, of course, is highly tailored to the distribution. So what this mechanism does, it replaces the reserve by a sampled signal, by the signal of the randomly chosen reserve bidder. Okay. So I'm going to talk about the revenue guarantees of this mechanism. So I want to quickly show what the payments look like. So first, notice that it is a monotone mechanism. So as the signal of the bidder gets higher, it's more likely to be in this potential winner set and more likely to clear the reserve. So that means that just applying the form of payments that we get from the Myerson theory, we get ex post IC and IR. So in particular, a payment will look like this. You take the value of bidder I, you plug in the signals of all the other bidders, and then instead of his signal, you plug in the threshold signal, which means the smallest one with which he still wins. So here, in order to win, you have to first clear the reserve, be higher than R's signal, and then also be part of W.
Yeah, if you pick the bidder who's picked to be the reserve,
yeah.
Nobody clears it, he gets it at that price?
No, he doesn't. The reserve, well, actually, so the way I described it, no, but I'm going to show you in one of the next slides, but I can just say it now. It happens only with probability 1/n that the bidder with the highest signal gets it. So we don't worry about it too much. I mean, it's a bad outcome.
Only in computer science.
Only in computer science, that's true. But actually, you can modify the mechanism. I wanted to show like a clean statement, but you can easily kind of modify the mechanism and kind of always extract revenue.
Okay. It's very interesting, very clever.
Okay, yeah, oh, I forgot to mention, I'm sorry, this is really important, that, it's clever in part because it extends this mechanism by Pierpont, Dangoiton, and Nate, Roughgarden, and Yan. Okay, okay, I described the payments. I want to quickly show an example. So let's say we have 3 bidders and one copy of the photograph, and all the bidders have the same value for the photograph. So it's a pure common value auction. The value is just a sum of all the signals. Okay, let's see what the mechanism does. First of all, it picks a random reserve. In this case, it picked bidder 3. Now, W is going to just be bidder 1 because he has the higher signal. And in this case, bidder 1 clears the reserve, and he pays his value just with the threshold signal, which in this case is max between 2 and 3. Okay, and this is what I mentioned before. If you get the reserve bidder happens to be the guy with the high signal, then bad luck, you don't manage to get revenue. But this only happens with probability 1/n.
Sorry, do you mind doing that a little slower?
Of course.
Because I got confused by the common value aspect of the example.
Right. Okay, so let me do that more slowly. So again, I have 3 bidders and 1 unit for sale, and the pure common value in this case, I just picked it to be the sum of all the signals. So every one of these bidders, they value the photograph at 9, right? Okay. Now let's say I pick their under reserve. I get the my winner. He clears the reserve, so he gets the photograph. How much does he pay? So I want to look at his value with the signals of others are plugged in just as is. And here, instead of signal S1, I take his threshold signal, which is he has to both be higher than S2, right, in order to be in the set W, and also he has to be higher than S3 to clear the reserve. So in this case, the maximum among them is 3, and it's going to end up paying up 8. Okay, now I think you kind of maybe are starting to see what could go wrong here. So, okay, I wanna, from now till the end of the talk, I'm just gonna assume that S1 is the largest signal and Sn is the smallest. Okay, so everything is renamed. Okay, I have 2 bidders and I have 2 units, 2 copies of my photograph, and I have a pure common value, which is the sum of the signals. Okay, now bidder 1 happens to have, this is going to be a slide without distribution, okay, just to get the idea. Bidder 1 has a really, really high signal. So notice what's going to happen. So this is the only way we can extract revenue, right? If this bidder is picked as the reserve, this guy's picked as the winner. But notice how much he pays. He only has to clear somebody who has a signal of 2, so he ends up paying 4. Now, do any of you see a way to extract a lot more revenue? Truthfully. So remember, we have 2 bidders. Their values are both S1 plus S2. And you're the seller, so you get reports of S1 and S2. You want to extract a lot of revenue, but you want to maintain truthfulness. So in particular, both bidders value the item at 10 million and 2. Okay. How much can you charge the second bidder? Second bidder says his signal is 2. But you know that the other guy's signal is 10 million. So you can just kind of charge him 10, yeah, exactly. You can just kind of charge him 10 million. And notice this is perfectly truthful, right? There's nothing he can do to kind of avoid being charged this high price. Okay. So, and this all happened because of this common value, like you were saying before. Now I want to show you the same thing with distribution, okay? Okay, so let's see this more generally. So again, the value is the sum of the signals. The signals are drawn IID from sound distribution. Now, the optimal revenue you can get because of this trick that I just described, like charging each one the other guy's signal, you can get very close to the expectation, S1 plus S2. However, if you use the single sample mechanism, then your threshold is always the second highest bidder. So you get, as your revenue, something that's like the expectation of the second highest. And the bad news is that if G is long tail, there can be a huge gap between the expected value and its second highest expected value.
Is it the expected value or expectation of the sum of them, the optimal revenue?
So I guess it's equivalent. I mean, up to like a factor of 2. So if you take,
If you're
yeah.
talking two players.
If I'm talking about 2 players, right. Oh, I need to, right, I see what you're saying. I need to think about it. But still, for this example, it gives, it's up to a factor of 2, and that's like what I wanted to demonstrate. The gap is really large. Okay. So that means that we kind of need this MHR condition, and just what I'm saying on this slide is basically that for MHR it's not hard to show that you can kind of, the gap between expectation and second highest is not large. And this is kind of inherited from the exponential distribution. Okay, but it's okay because it's part of the local conditions. Okay, now in the time I have left, I want to quickly show you a proof of our main theorem that the single sample mechanism gives a good revenue guarantee. So our main lemma is
Ask a question.
sure.
The last slide that showed that the single sample doesn't do as well as this other natural, was it prior free or not mechanism?
I guess it's even. You can say it's like prior free.
Yeah, it seemed like it was. At least if it wasn't prior free, it could be made prior free, probably.
Right.
It makes me wonder why we're analyzing the single sample mechanism. And not this other
Definitely.
one.
I think it's an excellent, open question. Can you, for general, regular, let's say even regular, do you really need MHR? That's, I guess, the open question. So we couldn't come up with a mechanism, but we definitely, didn't think about it enough. And I think this is kind of first step towards the right direction, but I think there's a lot of potential here for managing to come up with a mechanism. You know what? Even like I mentioned before, even a mechanism that's not per independent, and as well for independent for interdependent values where we have regularity, that would also already be interesting in my opinion.
Can you go over the MHR condition again?
Sorry, the MHR, of course, yeah. Sorry, I just went over it quickly. Because I didn't have much time, but I mean the proof is not complicated. So
Yeah, I was thinking and I just didn't even read it.
Yeah, I'd rather get this
Yeah,
slide.
let's keep going.
Oh, let me spend another few seconds on this. So MHR distributions are like a subset of regular distributions, and they're a pretty rich subset, even though they guarantee a lot. Like they don't have a long tail, but they're still pretty rich. Like they have the exponential and the uniform and the normal distributions are all in that. And we use MHR only in the sense that it guarantees us, because we don't have long tails, that expectation and expectation of second highest among two samples are pretty close. And actually they're like a factor of, for exponential distributions, it's just a factor of 2. Okay. And that's why, having this as part of the conditions we assume kind of solves the bad example we saw before. Okay, so let me see. Our theorem is based on the following lemma. So what you see on the left-hand side, we have two signals, S1 and S2. They're drawn IID from distribution G, which is MHR. What you see on the left-hand side is the expectation of the value. When I plug in the smaller among the two signals, right, S2 the smaller, twice. And what you have on the right-hand side is just the expectation of the value. And what I want to claim in this lemma is that plugging in the smaller one twice doesn't, ruin things too much. I still get kind of a comparable to expectation. So it's kind of similar to a small gap between expectation and second highest, but we have this extra value function. Okay, and just to show quickly the idea of the proof. So we need to get rid of the fact that we have twice the smallest signal, and the way to do it is just a trick of replacing by the median. So notice this is only in the analysis. It's not like I'm assuming that the mechanism needs to know the median. But in the analysis, I can kind of replace the first signal by the median, just because I condition on both signals being higher than the median, which happens with probability 1/4. Okay, this is what I get. Now, moving on, I can kind of get rid of the fact that now that I have only one S2 here, I can kind of get rid of it because I have the MHR assumption and I know second highest and expectation are close. And now I use an observation that the median actually is a very good reserve price in terms of how much revenue it can extract. And for MHR, being a good reserve, extracting near optimal revenue means you extract near optimal welfare, and that's kind of what gives me the final thing that I wanted in the statement of the lemma.
Are you assuming V is just S1 plus S2, or can you go general?
I'm assuming V is general, but I do need like the low POMO thing. So for example, this multilinearity of V I'm kind of using it heavily here. I don't want to go into the details, but yeah.
I've got a question just at the very first step.
Yes.
So if I've already sorted S1 and S2, then S2 is less than the median.
No, not necessarily. I mean, it could be that you randomly draw two signals and both happen to be higher than the median. It happens with constant probability of 1/4. So you need the first one to exceed the median and then the second one.
Under MHR then?
No, I mean just because of the way I define median. So if I
Okay, yeah.
Okay, so it's like it's a nice trick. Maybe you guys can find like applications for it. Okay. Again, this is kind of just showing how the lemma proves the theorem. So notice that if we have two bidders, like in the example we saw before, then really I exactly need the lemma, right? So what I have on the left-hand side was almost exactly the expected revenue, right? I plugged in like the threshold signal twice, and then compared to the expected welfare. And going from n bidders to 2 bidders is not hard just by kind of conditioning on all the bidders that are not the highest and second highest bidder. So I'm kind of hiding a lot of things, but really for a single item, it boils down to this. Okay, I want to wrap up. So here's my take-home message from the second part. As I mentioned, for multi-parameter settings, we have kind of really impossibility results that we can't really hope to get anything if we have these robustness requirements. But for single parameters, we can actually get a considerable level of robustness, even beyond IPV. And what's nice is that it kind of raises new challenges. So this whole MHR thing, it never came up in previous work on prior independence in the in IPV model. Okay, so I want to conclude. Any questions before this? Okay, so let's see. Okay, so what I wanted to claim in this talk is that interdependent values can, first of all, be a much better model of values in some settings, in some kind of real-life high-stake settings. This work kind of makes first steps toward extending the rich theory that we have, which is IPV-based, towards interdependent values. And so, in particular, we gave conditions under which Myerson-like mechanism, robust in the sense that it's exposed ICIR, exists. And then we kind of strengthened the robustness, and we showed that even after strengthening, you can get prior independent mechanisms in some settings. Okay, so here's the open questions I think can be kind of continue this work. So there are 3 directions. So first of all, optimal and near optimal mechanisms. So what I showed had a lot of assumptions. Can you weaken them? And in particular, here are 2 questions. So in the IPV model, if we don't have the assumption of regularity, we can perform ironing. And that's what Myerson does, and he gets a general result with no regularity assumption. Can you do anything like this in the interdependent model? Now, I know it's not, I expect it's not going to work always because of the hardness results, but when can you get it to work? What kind of ironing do you need? And I can talk about this in more detail offline if anybody's interested. Also, this question that I mentioned, that for just correlated values without the full interdependence, there's a really cool approximation mechanism that works without any assumptions. So can we develop something like this for interdependent values, or even take a few assumptions but weaker? Okay, different directions would be more applications. So just pick your favorite application for IPV. It doesn't even have to be an optimal mechanism design, and try to apply these tools and get something for interdependence. And finally, so I discussed robustness, and so I showed like these two, we talked about Bayesian versus ex post, but there's a whole range in the middle, and probably on one side at least, you can also consider all of these kinds of robustness guarantees. So what makes sense economically? What can you get technically if you look in this range of robustness? Okay, that's it. Any questions?
So I have a question about the prior independence section. So in environments where you assume the players have signals, and then you map those signals to a value with a value function, I feel like maybe your mechanism needs to know the value function already, and so it's not sort of independent with respect to the value function. And I'm wondering if there is a natural mechanism where the designer doesn't need to know the value function.
Yeah, I think that's a great question. I don't know. We were thinking maybe somehow use the English auction and assume like symmetry on the value functions and kind of get prior independence with respect to values. That would be awesome. I don't know. Anything else?
Any other questions?
Okay, thanks a lot.
Thanks again.